Hi, this is lesson 21 in the use of JASP for understanding statistics. And today I want to talk about the difference between common factor analysis or exploratory factor analysis versus principal components analysis. So let's jump into it. I want you to start by pulling up a data set in JASP. Go over to Open Data Library, and then go to Factor and Mental Ability and pull that up. I've already done that, and so my data set is here. One thing that I've done differently is I've gone ahead and changed the names of the variables. They were labeled X1, X2, X3, all the way to X9. I've relabeled them so that they have names that we can follow. For the first three, which get at visual ability, or sorry, spatial ability, those are being done by looking at how people rotate in space, various types of figures, and put an F for figures. Not the best thing, but I wanted it different from the S over here for speeded processes. So the S over here is for speeded processes, such as how fast can you add numbers together, how fast can you count, how fast can you make discriminations between various types of objects. And then, very important in the area of mental abilities and IQ is verbal ability, which is often said to be the best predictor of IQ. So verbal ability in terms of paragraph comprehension, sentence completion, and word meaning. If you want, pause here, take a moment and get your names aligned with what I have, then start back up and we can move forward. Okay, so let's go to factor analysis, and we're going to start off with exploratory factor analysis. And for this exploratory factor analysis, what I want to do is just go with not all of the items, but I just want to start with the verbal and get the paragraph comprehension, sentence completion, word meaning, place them over there, and it gives me factor loadings and uniqueness values. It says I'm counting for 71.9% of the variance in those three measures with a common factor. Only one factor, so everything here is pretty simple. I want to go to output options. And over here, I want to click on the path diagram. And I want to talk a lot about this path diagram because it's key to the comparison and distinguishing it from principal components of analysis. This model is saying that there is a common factor. Think of it as verbal ability. It's an unobserved construct. That is, we have no direct measure of it. Our measures are over here. But the idea is that one's verbal ability, if they're high in verbal ability, that would cause them to do better on word meaning. It would cause them to do better with sentence completion. It would cause them to do better with paragraph comprehension. And if it's causing multiple measures, then we can derive from the assessment of those multiple measures an idea of what this common construct looks like. And we do that by looking at these loadings. And the loadings, the strength of these links is shown up here. Those links can be thought of as the correlation between the common cause construct, which is unobserved, and the measure. And so the highest correlation here seems to be with sentence completion. And the lowest is with word meaning, but you'll notice that if you add another variable, sometimes that flips around and looks a little bit different. But those loadings are all pretty close to the same, no big differences there. Okay, that's exploratory factor analysis. Let's go back up, click on factor analysis again. We're going to go to principal components analysis. Principal components analysis, you'll notice that the layout here is very, very similar. And we're going to get our 3 verbal items, verbal ability items, load them in there, we get our loadings, and here it's accounting for 81.3% of the variance, the one single factor RC1. Go to output options, do a path diagram. Okay, this model looks very, very similar to what we saw with factor analysis, and the structure is really the same, but there are a few differences. I'll come back to talk about those few differences when I go through some other slides. But what I want you to notice most importantly is that the direction of the arrows is changed. Here, you have the uniquenesses associated with these measures being funneled into, along with the measure itself, that captures the factor to define the principal component. So we, instead of calling it a common factor in principal components, we call it a principal component. Now, to the untrained eye, just flipping the arrows seems to be just a matter of convenience, it's a matter of art. But mathematically, there's something very different going on here. And what I'm going to try to explain is that while there's, in some respects, something very different in reversing those arrows, that you could say almost totally changes the way that principal components and common factor analysis works. At the same time, the solutions that are derived from these two techniques are in many respects more alike than they are unalike. Now, let's go back and think about what's going on with the exploratory factor analysis. And what I want to do to get us there is I want to go away from that for a second, and let's focus on a different problem. Let's say I did a study and I found that there was a correlation between sales of ice cream, how many units of ice cream were being sold in the city, and violent crime. And I found that that correlation was 0.213. Here I have an R subscripted ice cream with violent crime, 0.213. That's the correlation. Now, if you have that correlation, you could think, is ice cream a cause of violent crime? Well, that seems really unlikely. Does violent crime cause people to go out and buy more ice cream as some kind of comfort? I don't think so. I think they'd be more likely to go out and purchase Ring doorbells and security devices. So what's the cause of that correlation? Well, it might be that they have something in common, and you've probably heard of this before in terms of the notion of a spurious correlation. It turns out this is kind of a common example that's often used in statistics because it has some true life validity. Not that we know much about the true correlation between ice cream and violent crime, because no one really studies that. But there are business studies that show that as temperature goes up, sales of ice cream go up. And in fact, that correlation is very strong. So that 0.69 is actually inspired by the true life correlation in the actual true research studies. It's also been found in true research studies that temperature has a moderate correlation with episodes of violent crime. People in the summer are more likely to be out, get hot and bothered, get into fights and so forth for a variety of reasons. Temperature going across the seasons, summer tends to give you somewhat more violent crime than not. Now, this model can be thought of as an explanatory device for the correlation between violent crime and ice cream. And there's what's called tracing rules, which I will not try to bring any depth to here. But the tracing rules basically say that if I want to know the correlation between ice cream and violent crime, and I have a model that a statistical model that tries to explain that, I can go back through an arrowhead over to another construct, change directions once, and go over to the other construct. And if I find that there's a link between the two variables via those tracing rules, I can take these two coefficients and multiply them together to see if that reproduces the correlation. And you'll notice that when I do this, I'm coming very, very close. I'm getting a correlation of 0.193. So if I take the actual correlation of 0.213 and subtract the model implied correlation that seeks to explain that correlation, I get a residual that's very, very small. Okay? So that is how correlations work with the common cause model. Now, let's go over here back to our common cause factor model, and I've taken some of the pieces of information from our output that we looked at. I've added in the correlation matrix. This is a very simple model. In fact, it's so simple that if you take out the rounding error, you can take these factor loadings, like the sentence completion. I put it here where it has sentence. Paragraph comprehension here for paragraph comprehension, and the 0.832 with the words. Now, these are factor loadings. Mathematically, they're referred to as lambdas, and lambdas start with an L, loadings start with an L, so everything is copacetic. That's all good. Now, it turns out that the type of math that we were doing previously can be used here. If I want to know the correlation between word meaning and sentence completion, I can go from here down to the common construct, change directions once, and go here, and that implies that I can multiply these two together to try to reproduce the correlation. And it does. 0.7205 reproduces the correlation of 0.720. And that works out for each one of these correlations. Each link, like from sentence completion, going back through this link and then over to this link, is 0.866 times 0.847, which reproduces the 0.7335. Now, what's interesting here is that there was never any real correlation between these. The way that is, there was never a factor loading. Remember, a factor loading is the correlation between the common cause construct and the measure. But this is unobserved. So how do I have a correlation? Those correlations actually came about by taking this math in reverse. That is, we said, here's the correlation that needs to be reproduced. So I'll find these loadings that can reproduce this correlation. And the loadings are basically chosen to reproduce all three correlations. You have three correlations, which are your knowns, three loadings, which start off as being unknown, and with three knowns, you can take three unknowns, draw out equations, and you can solve for the factor loadings. Those factor loadings hence are designed to reproduce the correlation matrix. And with only three items, it does so perfectly. And the more items that you add in, the less perfectly it does that. Okay, so common factor analysis gives us a set of loadings that are designed to reproduce the correlation matrix to find the hypothetical composites that causes the assessment, thereby separating it from the error. If you look at tracing rules, one thing about tracing rules is you can't start off with something over here, a source of error, through the arrow, and then enter back through an arrow. That's not allowed. So I've effectively, so these arrows, again, refer to mathematical rules that basically say that what's going on here is that I'm partitioning the errors from the construct. Over here, the opposite is occurring. The errors can flow into the construct. So three things I want you to notice here. The differences in how we draw the arrows, the fact that the common cause solution yields variance of 0.403, so it accounts for 40.3% of the variance in these six items, six measures. Principal components analysis, its goal is to maximize the variance that the assessments capture in a single composite, whether the variance is common or unique. And by doing so, by focusing on maximizing the variance, it does better. Over here, this 0.479, higher than the 0.403. It does that by giving us loadings that over here tend to be higher than the loadings over here. Same structures, but slightly different loadings, capturing those unique effects to actually maximize the variance more. Let's go back over to JASP. I want to go ahead and add in for our exploratory factor analysis the spatial ability that I have noted as figures. And you notice that what the model really wants to do, what it naturally does, what is much better fitting model, is for it to load onto two factors. So that means that there's one factor, there's actually something called verbal ability that is separate from our ability to manipulate figures in our heads. Those are two constructs. They're related. You can go to the output options and look at the factor correlations and see that they're correlated at about 0.410. But it's two factors. But what I did for the previous slide was I forced them onto one. I said, give me manual one factor, forced them all onto one factor, it's not remotely as good of a model. And in order to see the factor loadings, I had to lower this bar over here to display more factor loadings, getting factor loadings that are generally considered unhealthy. When I look at the principal components, let's go back over here to principal components, do the same thing, add in the figures. Again, it wants to be two factors. It says with two factors, it can account for 70.2% of the variance in all of these items, indicating that there really is some separate variance to be had there. But again, I'm going to force it into a bad model with just one factor by clicking on the manual. Number of factors equals 1. And there's my loading, and it's only doing 47.4% of the variance. So again, principal component is trying to maximize the variance with its loadings that don't separate the measures from their unique effects, whereas exploratory factor analysis is saying, okay, maybe IQ is a cause of all of the performances on all these measures, but there's also other things that are causes of these measures. One of them is that spatial ability is different than verbal ability, but also that your ability to know word meanings is not simply due to IQ. It's also due to things like where you went to school, what kind of vocabulary your parents used, and so forth, right? So there's other causes, but those are being separated in exploratory factor analysis. Here we see it again, and in this case, you can think of the principal component as being right about here. But you'll notice that I've drawn the arrows to basically say that in deriving the principal component, the math is designed to kind of stretch out beyond the factor itself to try and capture some of the errors or uniquenesses from each of the measures. So each of the measures represents overlap, and we're very interested in the overlap. That's how we get a common factor or a principal component. But the principal component is kind of stretching past the common factor to incorporate as much of, maximize getting as much of the variance as possible. In exploratory factor analysis or common factor analysis, there's the common factor, and we don't stretch beyond the common factor. The goal is to separate the common factor from the unique effects, from the errors that occur. I'm going to close with an analogy. This is my longest video yet, but I think this is an important topic, and it's something that's really hard to think about, but so maybe an analogy will help. Analogies are always a bit imperfect, so this is an imperfect analogy, but let's go with it. So common factor analysis is basically, let's imagine that you want to know what pollutants are caused by this main river that define or characterize the main part of a river. So you have this river, but you can't get to the river up here to measure it. So up here is this, the beginnings of the river, the source of the river, and you're wondering what pollutants are define that river. And what you can do is you can go to these little ponds and lakes that are offshoots of the river, and And let's say you can reach those points and you can measure those. And when I go to this one, I measure and I get mercury and cadmium. So that suggests that this river might be containing both mercury and cadmium, but there's also a little stream over here, and who knows what it's contributing. So I go over here, and let's say in this one I find mercury and iron. There's a little tributary that also empties into this little lake. And so, what's the nature of this river, right? Now this tributary ends up in this pond and can't go back in, so the source of the error cannot go back into the river. That's important for the analogy. Over this one, we find mercury and arsenic. And down at the bottom, still another tributary, and we find mercury and copper. Now, logically, what's common to all of the measurements is mercury, which suggests to me that what defines the pollution in this main river coming from its source, the common source of the pollution, is mercury. And I have to consider heavily the possibility that the cadmium is produced by this tributary, the iron by this one, the arsenic by this one, the copper by this one. But it makes sense that I can thereby deduce, removing the error, that what the nature of this river is mercury. That's common factor analysis. Principal components analysis, again, is asking a separate question. Let's say I get measures here, measures here, measures here, measures here, measures over here, measures over here. They line up with these over here. But in this case, the little tributaries are flowing into the river. There's no place to separate the tributaries from the main river. So I might find that cadmium is being run through here and lead over here and so forth. The point is that principal components analysis just wants to describe the whole river system. It's not treating those other measures as pollutants. So it might be that the largest pollutant in the river system is mercury, because mercury is the biggest river in this system. But principal components is basically saying, that's okay, I'm just trying to explain as much as I can. And so if there's cadmium in there, iron, arsenic, and copper, all of those are part of the pollution in this river. Okay. One last time. The goal of common factor analysis is to separate the errors from the common factors so that we get a pure estimate of that common cause construct, whereas principal components is doing a lot of the same work, which is why you get the same overall solutions, but the loadings tend to be a little bit higher because it's stretching through to capture as much variance as possible, not trying to separate the common cause factor from the uniquenesses, but just to summarize that variable as much as possible. Psychologists would view that as very pragmatic, almost too pragmatic for most of the work that we do. Since most of the work is theoretical, we're interested in talking about those common cause constructs, and hence exploratory factor analysis rules in psychology. Principal components analysis takes a major backseat. Thanks for your attention. Bye.